Okay, today's topic is phasor diagram of induction motor. In previous class we have studied about the equivalent circuit of the phasor diagram, equivalent circuit of the induction motor. Now we have got three equations from the equivalent circuit, and they are V1 is equal to minus E1 plus I1 R1 plus I1 X1. All these are phasor quantities. So here E1 is the EMF induced in the stator of the induction motor, and it is in opposite direction to the applied voltage. I1 R1 is the voltage drop across the resistance, and I1 X1 is the voltage drop across the reactance. Now the supply voltage V1 has to compensate all the voltage drops as well as the E1 in opposite direction. E1 it has to counterbalance this E1 as well as this voltage drops. This is, let us take this as equation number 1, and then the EMF in the rotor, the induced EMF in the rotor under running condition is E2R. Now in the rotor we have the current as I2R, which is rotor current under running condition, and E2R, the EMF, the induced EMF in the rotor has to balance the voltage drops in the rotor. And in the rotor again we have the voltage drop across the resistance R2 as well as the rotor reactance X2. So the voltage drop across the resistance is I2R R2 plus I2R X2. And here this is the reactive part. So this is a complex number equation. So here the J is written here, and then we have one more equation, that is I1 is equal to the total input current to the induction motor is I1, which is equal to I0 plus I2R dash. This I0 is the no load current to the induction motor, and I2R dash is the load current to the induction motor. And this dash is because when we shift the secondary parameters or the rotor parameters to the stator parameter, we have taken this as dash. This is equation number 3. Now using these three equations we are going to draw the phasor diagram of the induction motor. Now let us take phi as the reference phasor. Now this phi is the induced flux in the induction motor. Now this flux is because of the current, okay, because of the magnetizing current Im, okay. Now this is because of the magnetizing current Im, so obviously phi will be in phase with the Im. Now this Im and the applied voltage V will be 90° apart, and obviously V will be lagging behind the flux by 90°. So here we get the E1. This is induced EMF E1, okay, which will be lagging behind this flux by 90°. Okay. Now this is E1, and we know that E1 and E2 will be in phase, and now will E1 and E2 will be in phase. Now let us consider this I2R, the rotor current under running condition, and since it is in induction motor, current will be always lagging behind the EMF by some angle phi 2R. So let us take this I2R here, which is lagging behind the E2. Now E1 and E2 are in phase, so here I am showing this I2R which is lagging behind the E2 by an angle phi 2r. Now this is E 2r. Now after this, we know that E 2r is I 2r R2 plus j times j I 2r x2. J I 2r x2. So I 2r R2 will be in the same direction, will be in phase with the I 2r. So here I extend the line, and this is I 2r, this is I 2r R2. Now this is I 2r R2 plus j times I 2r x2. J times I 2r x2 will be 90 degree to this I 2r line. So here I have j times I 2r x2, and this is nothing but our E2r. Here we have the E2r. This is E2r. Now I2r is here, and we also have the equation, that is I1 is equal to I0 plus I2r dash. Now before that, we have to have this I0. We know one more equation, that is I0 is equal to IC plus IM. That is, this is the magnetizing current, and this is the current required to compensate the no load iron losses. So I0 is equal to the no load current. Under no load condition, the current required by the induction motor would be I0, which is equal to IC plus IM. IM is the magnetizing current, and IC is the current required to compensate the no load iron losses. And here we have the IM, and this IC will be 90 degrees to this IM. So this is IC here, and the phasor addition of this IM and IC will get us the I0. So this is I0, and by extending this I2r in opposite direction, we'll get the I2r dash. So here we have I2r dash. Now we know that phasor addition of this I0 and I2r dash will get us the I1. So phasor addition of I0 and I2r dash will get us the I1. So phasor addition of these two is like this, and here we get the I1. This is I1. Now we want the equation 1 to be represented in the phasor diagram. V1 is equal to minus E1 plus I1 R1 plus j I1 X1. Here we have the E1. By extending this in opposite direction, we get the minus E1. So in the opposite direction, extend the line E1. Here I get minus E1. This is minus E1. Now the equation is V1 is equal to minus E1 plus I1 R1 plus j I1 X1. So this is minus E1, then plus I1 R1. In the same direction of the I1, from the tip of this, we'll put a line which is I1 R1. So this line is in phase with this I1. So this is I1 R1, and j times I1 X1 will be in 90 degrees to this I1. So this is j I1 X1. So from the center, if I draw a line to this, this is nothing but V1. So V1 is equal to minus E1 plus I1 R1 plus j I1 X1, and this is the phasor diagram for induction motor under loaded condition. I repeat this here. Initially we have to take the flux as the reference phasor, and this flux is because of the magnetizing current Im. So this Im and flux will be in phase, and the induced EMF E1 will be lagging behind the flux by 90 degree. So show the E1 in the downward direction, and we also know that both the EMFs, both the stator EMF as well as rotor EMF will be in phase. So E1 and E2 will be in the same direction. Now before writing that E2, first we should be considering the I2R R2 plus J times I2R X2. So I2R is in this direction, I2R R2 will be in the same direction, J times I2R X2 will be in 90 degree with this I2R line. So this is the point where we get this E2R, because E2R is equal to I2R R2 plus J times I2R X2. Now extending this I2R in the opposite direction, we get this I2R dash. Now this is I2R dash, and we also know that I0 is equal to Im plus Ic. Now one more equation, that is I1 is equal to I0 plus I2R dash. Here we have the I0, here we have the I2R dash. Phasor addition of these two will get us the I1. Now we have the equation, that is V1 is equal to minus E1 plus I1 R1 plus J times I1 X1. Here this minus E1 is drawn in the opposite direction to the E1, because this is minus E1. Extend the E1 in opposite direction, we get the minus E1 plus I1 R1 is in the same direction as that of the I1 from the tip of E1, and then J times I1 X1 is 90 degrees to this I1 phasor. So this is I1 J I1 X1. So from the center draw a line to this tip of J I1 X1, and that gives you minus E1 plus I1 R1 plus J I1 X1. That is the final V1. This is the phasor diagram of an induction motor under loaded condition. Now moving to the next topic, that is circle diagram of the induction motor. In a particular circuit, if any one variable element changes its value, then remaining all parameters will be dependent on the particular value, okay, will dependent on the previous parameter, okay. Like for example, in an RL circuit, if R changes its value, then the current or the voltage drop across the resistance, so many other parameters will get changed. Similarly, here we are considering this circle diagram because we are planning to do this because this induction motor changes its parameters like current or the input current, because if the load changes, then the input current will change, and if the input current changes, then so many other parameters will get changed, like the losses, like the torque, and so many different parameters will change. So here, by plotting the circle diagram, we are going to guess that what will be the losses, and hence the efficiencies and torques and different losses like iron losses, copper losses. We are going to guess them or calculated them in advance without actually loading the induction motor. Now here we can say that the locus of the extremity of the current phasor, the locus of the extremity of the current phasor. Let us take that this is the current phasor. Now the locus of the extremity, like if this is the current phasor, if these are the current phasor, now the extremity, the locus of the extremity of the current phasor for the variable parameter is called as the locus diagram, okay. And in case of induction motor, as the load changes, current will change. If the current changes, then obviously all other parameters will change. And in case of induction motor, even we can consider this the induction motor as a series RL circuit, because again in the induction motor we have the resistance. In both stator and rotor we have resistance and reactance. So obviously an induction motor can be considered as a series RL circuit. And in case of induction motor, this locus diagram is a circle, so only this is called as a circle diagram, okay. Now we have few equations here which will help us to draw the circle diagram. Here first we'll consider the equivalent circuit of the induction motor. Now to draw the equivalent circuit of the induction motor, here first we'll have the resistance of the stator, that is R1, and the resistance of the rotor. Together we call them as R1E, which is equal to R1 plus R2 dash. And then we have the reactance part, that is X1, the stator reactance X1 and the rotor reactance X2 dash. So together we are going to call them as X1E. And then here I show the variable load, and here I show the basic primary magnetic circuit, that is R1, R0 and X0. Let this be the R0 and let this be this X0. This is the total no load current I0, and this is the total current I1, and this is the current in the rotor circuit, that is I2R dash. Now the current in this is IC, and this is the magnetizing current IM, and here I complete the circuit. This is V1, the input voltage V1, and the I2R dash I have shown here, I2R dash. Now this is the equivalent circuit of the induction motor. Now if I write the rotor current I2R dash, which is equal to V1 divided by the total impedance Z1. The total impedance Z1, which is equal to V1 divided by, sorry, I have to write the load resistance equation, that is R2 dash into 1 minus S divided by S. We have already derived this. Now this Z1 can be written as R1E plus RL dash square plus X1E square. Now this is nothing but, this is the total resistance in the circuit, and X1E is the total reactance. the total resistance is R1E plus this thing I am considering, this is nothing but the total load resistance RL dash. I have taken this as RL dash, and X1 is the total reactance. Now this can be, before that let us multiply and divide the same equation by X1E. Multiply and divide the equation by X1E. Now by doing that we'll get I2R dash is equal to V1 divided by X1E into X1E divided by R1E plus RL dash whole square plus X1E whole square. Okay. Now this V1 by V1 divided by X1E is nothing but the maximum current I max, and X1E divided by the square root R1E plus RL dash whole square plus X1E whole square is nothing but sine phi. So here again I can write this I2R dash as I max into sine phi. Here this V1 X1E is written as I max, and this X1E divided by the impedance is written as sine phi. So this I2R dash is equal to I max into sine phi. Now here I'll tell you why this locus diagram is actually called as circle diagram, because the equation for the I2R dash is having the trigonometric function sine phi, I max into sine phi. So if it is, since it is associated with the sine phi, obviously the locus diagram for the induction motor will be circular in nature, so only it is called as a circle diagram. And here I'll show you how actually it looks like. This is actual short circuit current, and this is I max ideal short circuit current. This is V1, this is current axis. Now here this in this particular equation I2R dash will be maximum. This will be maximum only if R1E plus RL dash whole square, this particular term, is equal to 0. This will be maximum if this becomes equal to 0. That is R1E plus RL dash is equal to 0. And this condition R1E and RL becoming 0, that condition is called as short circuit. Okay, that is short circuit. Under this condition there will not be any resistance, and the phasor diagram for that is shown here. And here I am joining all the extremity of the locus, extremity of the current phasors, and this becomes a circle. So only this is called as circle diagram. And here the condition is, here we are considering only the secondary current, that is rotor current, which is I2R dash. But for an induction motor, we know that the total input current I1 is equal to I0 plus I2R dash. The total, I repeat, the total input current to the induction motor is I1, which is equal to I0 plus I2R dash. Whereas where this I0 is nothing but IC plus IM, which is IC is the current required to compensate the iron losses, and IM is the magnetizing current. This I0 is a constant. It's a constant. Okay, it's a constant. Only thing is I2R dash is changing. It's a variable. Now because of this, the entire I1 will also get changed. So only this circle diagram should also include this I0, but which is a constant. So only this entire circle diagram gets shifted by the value I0, and this also depends upon the power factor. So only the rough circle diagram which I can show you here is, this gets shifted by a value I0, and instead of using this particular axis, we'll use a new line, whereas this will become I2R dash. Now from here we'll draw the circle diagram, and below this all these will get us the constant losses, or all those constant parameters. We can find them below this line. In between these two axes we'll find out all those constant parameters, and above this we'll get all those parameters, variable parameters, using this circle diagram. Now this is about the introduction of the circle diagram. Now let us actually study how this actual diagram can be drawn by conducting an experiment. Now to begin with the conduction of the experiment, the circle diagram experiment, we need to have different parameters which can be found by conducting two experiments. One by conducting no load test, and one more is by conducting blocked rotor test. Let us see the circuit diagrams for no load test and blocked rotor test. To conduct this no load test on the induction motor, we'll use this particular circuit. Let this be the three-phase supply, and from here we'll connect two wattmeters in the circuit. Let this be wattmeter 1, let this be wattmeter 2, and these are the phasors, so phases RYB. Now here we'll put an ammeter, and here we'll put a voltmeter between any two phases, and then connect them to the induction motor. Now, to conduct this particular experiment, keep the induction motor under no load condition, switch on the three-phase supply, and then note down the voltage, current, and the wattmeter reading. For that, we'll give you the table here, observation table. Here this is input voltage, and this is no load current I0, and this is no load input power W0, which is equal to W1 plus W2. Now under no load condition, we are going to run the induction motor, and we are going to note these meters values like voltmeter, ammeter, and the wattmeters. Here we'll get the no load applied input voltage, no load current I0, and no load input power W0, which is equal to W1 plus W2. Here W0 will be equal to root 3 V0 I0 cos phi naught, where cos phi naught is equal to W0 divided by root 3 V0 I0, where V0 and I0 are line values. This is no load power factor. Now I can write the equation for IC, IM, R0, and X naught. See, just by getting this applied input voltage, no load current I naught and the no load input power W naught, we can calculate these many parameters like the IC, IM, magnetizing current, R naught, the no load resistance and the reactance. For this IC, this is nothing but I naught cos phi naught, this is I naught sin phi naught, this is called as active component. Active component of load current, and I naught sin phi naught is magnetizing component of, sorry, this is no load current. Magnetizing component of no load current. This R naught is equal to V naught per phase divided by I naught per phase, which is no load branch resistance. This X naught is V naught per phase divided by IM per phase, which is no load branch reactance. Now, this particular W naught will consist few losses like stator copper loss, because anyhow under no load condition in the stator some current is passing, and that will have a small amount of copper loss, which is equal to 3 times I naught square R1. Now the stator, this particular W naught will consist of stator copper loss, which is equal to 3 times I naught square R1. This 3 is because it's a 3-phase circuit, a 3-phase induction motor, and I naught is the no load current passing in the stator, and R1 is the resistance of the stator. And it will also have stator core loss, or it's nothing but the stator iron loss. We know that we are considering only the iron loss of the stator, because in the rotor iron loss is very negligible, because it depends on the frequency, and the rotor frequency is very small. We know that it is Fr dash is equal to S times F, where S is the slip of the slip, and if you multiply the slip with the actual frequency, then Fr dash will be very much negligible. So we are not going to consider the iron loss of the rotor, hence only the stator loss is compensated, and here we know that this IC is the current required to compensate the iron loss, and this W naught is including that also, and here the W naught is compensating the stator iron loss. And the third one is, it is also compensating friction and windage loss. That means, and the second one was stator iron loss. Stator iron loss. That means under no load condition, the test which we are doing, that is no load test, will give us all these parameters like IC, IM, R naught and X naught, as well as we can calculate the stator copper loss, stator iron loss and friction and windage loss. That means by conducting no load test, we will be getting all these constant losses, because iron loss and friction and windage loss are considered to be the constant losses. So here, by conducting the no load test, we are going to get all these parameters as well as these constant losses. Now the next one is, as I have already said, we will be conducting two tests on the induction motor to draw the circle diagram. The next test is blocked rotor test. Blocked rotor test. Under this condition, the circuit diagram remains same. But in the laboratory, while actually conducting the experiment, we actually change the voltmeter and ammeters with different ranges. We use a higher range ammeter for the blocked rotor test and a lower range voltmeter, because while conducting the blocked rotor test, the applied voltage will be very much minimum, and hence a higher range voltmeter may not be that accurate. So only lower range voltmeter will be used. I guess all of you have conducted the experiment on this circle diagram, so you might be knowing that lower range voltmeter is used here, and a higher range ammeter is used for the blocked rotor test. Now to conduct this blocked rotor test, before switching on the three-phase supply, the rotor of the induction motor will be held tightly, and here we'll be using a dimmerstat in between the source and the actual induction motor, and three-phase supply is switched on, and using the dimmerstat, slowly the voltage across the induction motor is increased until the ammeter reads the actual rated current of the induction motor. I repeat, the dimmerstat value is increased, the dimmerstat is rotated until this particular ammeter actually reads the rated current of the induction motor. Suppose this is a 5 HP motor. For any 5 HP motor, the rated current will be around 7 to 7.5 amperes. Okay, so that means the dimmerstat here will be gradually increased until this ammeter reads 7.5 amperes. This is just an example. Okay, and at that particular point, this voltmeter may not be showing you the actual rated voltage, because this induction motor is not rotating. The rotor of the induction motor is actually blocked. Okay, so when it is blocked, it is as good as shorting the induction motor. So the supply given to the induction motor, the voltage supplied to the induction motor will be very small. Okay, so only for blocked rotor test, so for the blocked rotor test, the observation table will be no load applied voltage, that is, blocked rotor voltage, I'll write it neatly. And the blocked rotor current, that I'll call it as short circuit current, and one more is WSC. So here, by conducting by conducting this block rotor test, I'm going to get this VSC, ISC and WSC. That is short circuit voltage and short circuit current and short circuit input power. Now, by conducting this block rotor test, let us see what all parameters we will be getting. without actually conducting the experiment, we can predetermine all these parameters. Sorry, I repeat here. Here by WSE we can calculate copper loss of the stator and rotor, and R1E we are calculating. Z1E can also be calculated. By having these two parameters we can calculate X1E. So totally we are going to have all these parameters by conducting block rotor test. By conducting the no load test and block rotor test, we are going to calculate all the parameters like R1E, X1E, R0, X0, IC, IM, and no load test like iron loss, and also friction and windage loss, and these variable losses like a copper loss of stator and rotor. All these parameters can be calculated for the induction motor by conducting no load test and block rotor test, and also by plotting the actual circle diagram. By actually plotting the circle diagram, we are going to find many more things like the parameter like torque, and even in torque so many different parameters are there. So we'll discuss them in the next class. In next class I'm going to discuss how to construct the circle diagram. I'm going to explain the procedure of constructing the circle diagram step by step, and also will explain how to calculate all these different parameters. Thank you.